Welcome back, everyone. In this video, what we're going to do is go a step further with what we left off with in the previous video. Currently, what we're doing right now is we've got a single layer of inputs. And what I want to do today is actually expand that out to multiple layers of inputs and introduce batches and get into a little bit of object-oriented programming. And also start to talk about our activation functions. And so to summarize where we really are graphically, you see that we've got our inputs, our weights, and our bias. And we've got this single layer of those inputs. And we're using our dot product really to process the fact that we have an array of inputs with a matrix of weights, and then back to an array of bias, with the ultimate goal of actually coming out with a single array of outputs. And you can see here when we do the weights and inputs, and then we add the bias, we're coming with this array. Okay, so that's really where we are right now. But this really is just a single layer inside of our neural network. It's not fully complete. It's a single layer, but as you know from before, we have multiple layers. But the story is really incomplete when we're just looking at a single layer. And if you look at this example here, you're seeing the input layer, 3 hidden layers, and then the output layer in their weights and biases. And so when you look at this calculation on the left, you're seeing, a great number of different inputs and different features that we're trying to capture those inputs on. And so when you look at the number of pure parameters as your neural network gets bigger, it's really difficult to try to handle that hydraulically by typing in that stuff. So we get to a point where we want to start addressing this in terms of batches. So it really makes sense for us to do this in terms of batches, as opposed to trying to type these values in by hand. So what's happened is we have this single input here. Okay, and so I want you to try to sort of imagine in your head that this could be constant updating sensor data as an example. Okay, so let's say room temperature, light intensity, anything, maybe water temperature. Okay, so you're looking at something that has constant feeding of data, right? And so far, we've only really addressed the one input layer with this array, but it gets more complicated than that. So we're going to look at this idea of a batch. Now, suppose I do have one batch. This is just single inputs of a temperature sensor, okay? You're seeing that the line is starting to adjust to individual sensor inputs, one at a time. And you can see that our line, our boundary is moving around, and it's trying to fit inside that single batch, okay? And there's a lot of movement in that, but it's one at a time that it's coming in. And that's not necessarily the way, a neural network is best optimized. Okay, so this is generalization. We're generally trying to fit inside these individual samples that are coming in. Okay, so on a single batch, you see so much movement. It's not really the best way of going about this. So maybe we want to introduce multiple batches. Okay, so this would be a little bit easier. So now we're seeing 4 at a time, as opposed to just seeing 1 at a time. And this really talks about why in neural networks, people have gone to the GPU instead of the CPU. Just better graphic sensors or graphic processing of this data. And you can see that there's a little bit less movement in the line itself, but with 4 batches, it's better. And suppose we want to go to 16. Now we're seeing 16 samples come in at a time. And you could see the output of the line, what's happening there. Okay, and there's a little bit less movement as we go, but it's easier for our computers to handle that much data. And then again, we can take it one step further and go to 32 samples at a time. So we've got a batch of 32 samples coming in simultaneously. And now there's a reduction in the movement, and the line is trying to move around less, and that's better for us. Okay. And what does this really mean for us? So we're looking at this simple 1D array right now, and we have this shape, right? We're saying the shape is 1 in 4. And now we're saying 2, 3, 4 of 4. Okay, and now what do we have? We actually have this 2D array. This is the batch that we're talking about. And now we have this batch, right? This is the efficiency that we're actually talking about. I want my input data to come in now as a batch so that I can have a matrix being compared against another matrix that we have in our weights. Now, the one thing that we don't want to do is have an overwhelming size to our batches. Okay, so we really don't want to go and drop all of the data all at one time, because that's something called overfitting, and it's going to cause anomalous results in our data. So we don't want that to happen. Okay, but we want to feed in batches that are of sufficient size that are going to produce a good result. And in the future, we will get into loss and error rate and all that kind of stuff. But for now, just realize it's better to add in some batches, maybe to 32 or even 64, maybe 128. Okay, but again, that's something that a GPU would be better at processing than a CPU. But for now, we can live within whatever operating system you have or whatever computer you have for this. So no big deal there. So let's go in now and modify our inputs. And we need a square bracket here. And I'm going to put a comma on the outside of this. Now, normally, you know, in a big application, I'm not going to hydraulically be typing this in, right? I'm doing this for example purposes only. But we want to, like we've done in the past, where we're reading in a file of input data into the machine learning application that we're looking at. So just for the sake of this example, I'll do it hydraulically here, but in the future, we will get into reading from a file and looking at our samples and stuff like that in that manner. But for now, let's just go ahead and update this. So I've got the comma there. And what I want to do is my square brackets, because I'm going to add another set of numbers. So 2.0, comma, 5.0, comma, negative 1.0, comma, and 2.0. And let's go outside of that bracket and again, do another one. Square brackets again. And this one is going to be negative 1.5, comma, 2.7, 3.3, and negative 0.8. Okay, so, and then I need to finish off this batch with another square bracket. Okay, so if you look at what we have, we now have a matrix and we're going to use it against another matrix. Okay, so, you know, on balance, they're both structured, so their shapes look very similar. So at this stage, you might think, okay, I can go ahead now and run this. But if you attempted to do so, you would in fact get an improper output. And we're going to talk about really why that is. And because it looks like my inputs have the same exact shape of my weights. And that is in fact actually true. But what you're going to notice is that I'll get this error. So let me run it and I'll walk you through why I get the error. So I run through this and you see what's happening here. And I want to look at the shape here. You're seeing 3 and 4 and 3 and 4. But you get this error that says, hey, dimension 1 is not equal to 3. And what does that really honestly mean? And we're going to look at this because it's a really important thing to understand. What's happening is I've got this value, let's say my 0 index, and it's trying to multiply against this. It's trying to do its dot product. But then this one here, and now this 2 is trying to go after this value. This 3 is trying to address this value. And our intention is to have the 1 in the 0.2, 2 and 0.8, and so on. And so we need to really look at this from a couple of different ways. And we have these two matrices, and you can see that they're shaped, and we need to do something called a transpose. We need to reorder our columns and our rows in order to use this properly, because we want to move on to something else. Because we haven't done that yet, we have to do the transpose, because ultimately what we're trying to do is something that looks like this. Okay, we have a matrix here, and then we have another one, and you can see they have a different shape. Okay, and that's okay for what we want to do, but what are we ultimately after here? And it's where we're trying to line up our columns and our rows and do a dot product transformation and get an output. Okay, and you can see here we've got our first on our row, we're summing those, and the output is this 105 that you see. And then again, we're going to compare the column at the top right with the row at the bottom. And we're going to go through this process, okay? The computer, thankfully, is going to go through this process for us. And ultimately, what we really want to do is generate this new matrix, okay? And so we need to be doing transposition in order to make this all actually work the way we want it to, so that we can get the proper output finally. And we look at this, and even though they have a matching shape, they're just not transposed in a way that makes sense to us. And again, this is all we're doing, is we're just converting rows actually into columns. Now, this is a true technique or operation that is true for even computer vision when you eventually get into that. But this is an important thing that happens throughout machine learning everywhere. And luckily for us, we're no exception. And so how do we do this in a practical sense? How do we get the software to do transposition for us? So I hope that you understand I'm not going to hydraulically do this. I would never try to reorder the numbers to make it work for me manually. I'm going to let the software do this. And so when you consider that our inputs are a list of lists or a matrix. And under Python, that's acceptable. But now, because we're using NumPy, what we're going to do is convert the weights to a NumPy array. And this is really simple to do, very, very useful. So instead of a list of lists for our weights, we're going to convert it to a NumPy array. And this is a really, really simple thing to do, and it's just great. And so the way I want to do it is, in front of my weights, I just want to type np.array, put my weights into this bracket, and I'm passing it as part of the NumPy array method or function. And I'm just literally going to type capital T. Capital T is my transposition. And that's all I'm going to do with this. And so let me go ahead and now run this and run. And you see, I still have an error. And this error is, you can see it down here, operands could not be broadcast together with shapes 4, 4, 3, and what? And so one of the things I can do to resolve that now is just move around my parameter list. Put the comma in here and of course get rid of this one. And that should be it for this. So when I run this, now you're seeing that I'm matching up the shapes properly and I get this output. So I have now a batch of outputs that I can send into the next layer of my neural net. So let's talk about what really happened there. Why didn't this work? And this is what we have as our weights and our inputs, right? And you can see we have a 3x4, and then we have a vector with a shape of just 4, right? And then we have another vector. The output vector was just a 3. So those shapes actually didn't match up when we added the two batches together, right? So I got an input batch and a matrix batch. Well, I have to change the order of these things in order to make the shapes work again. And so this is really how we're doing it. We're just matching up the proper shapes between the two matrices. Okay, and then we get an output of a 3 by 3. So it's vitally important that we understand what this overall transposition does and how it creates this new 3 by 3 matrix. And so now ultimately this is what you're seeing is the 3 by 3 result of what we have just done. So what does that really look like for what we've done in our specific example? We've taken the inputs, the weights, the bias, and we've run it through this transposition in this manner here. And you're seeing now that we've reshaped it. We've transposed our weights into this new matrix. And now we're going to take the inputs and we're going to then create the dot product of all of that. And this is really what it generates for us, this 3 by 3. Okay. And that's a result of the matrix of the weights and the inputs. But what you'll note with mine is that it's a different matchup than what you just saw. It's because in my particular case, I still have to account for the bias. And so what does that really look like? And here we see that we've got our whole setup now, and we've done the dot product, we've transposed, okay, we've got that output, but now we actually have to add the bias. And so how does this end up shaping up? And you can see it right here. It is just really a 1-for-1 addition. That's all we're doing. And that's what our output is based on right now. And you can see here that matches up nicely. So I think the next thing that we want to do is actually add another full layer. Okay, and I can do that just by copying this here, the weights. Okay, we're going to say copy, go down, and let's just do this. And we're going to say this is weights 1. And of course, I need another bias. So I'll copy this. And what I'll do, I think, is just keep it simple. Keep them all matched up. And down here, I'll do bias, let's say 1 as well. And now I'm going to just kind of change the numbers. Okay, so let me go in and just really quickly update all of these numbers in our new layer of weights and bias. Okay, so that's going to be there. So those are now updated. Now it's important to understand that this is a second layer. And so we need to change this one here. So instead of just output, I'm going to say layer 1 underscore. And if I haven't mentioned it in this particular video, you'll notice that all this code matches up with the animations. And again, it is from the Neural Networks from Scratch book that I talked about in the last video. And if you buy the book, you can kind of follow along with this as well. It's all these numbers are in there, or just if you're more happier, follow along in the video. Okay, so we've got that done. And the reason I'm changing this layer 1 output is because I want to copy it. I'm going to Control C, not Control Z it. And I'm going to put this underneath. Okay, and here's the important thing. As you know, the outputs of this previous layer are going to become the inputs into my new layer. So if I copy that, sorry, I keep doing that. If I copy this, and now my inputs are the previous layer, you get to see how these layers are starting to line up. Okay, and so this bias needs to be biased 1. Okay, so now I'm going to be using this one because this bias and these weights were used to generate our very first output. Okay, our layer 1 output. And of course, now this needs to be changed to layer 2 output. Okay, and now, of course, in order to see that, I want to have this output here. Let's print this to the screen. So I'm going to run this and then run the next one. And you see again, I've got this error. That's okay. If you get this error, it's not that we're doing something wrong. What it means is that I haven't actually done the edits properly. Remember, there's a difference between weights and weights 1 now. And so I need to add my weights 1 to this. Okay, and then if I run this, now I have a different product altogether. Okay, so to be very, very clear about something, doing it in this fashion, this hydraulic kind of way, completely non-productive at all, right? And so one of the things that we can do to mitigate this is now convert all of this, convert our layer or our neurons to an actual object. Okay, so I think that's what I want to do next is now get into object-oriented programming using Python to do this. Now, I'm hopefully you're following along, and what I'm actually going to do is highlight all that and Shift and comment this out, because I'm actually going to get rid of all of that. Okay, and as we've seen previously, usually convention-wise, our inputs are a capital X. That's what we've done in the past. That's what we're going to stick to. And let me just tidy this up a little bit more. Okay. In fact, I think I'm just going to delete the entire thing. And so to begin the implementation of our class, we're if we think in what we refer to as these hidden layers, which is the layers between the input layer and then the actual output layer, those ones in the middle. And why do we say they're hidden? Well, in actuality, it's because we don't necessarily control what goes in. Like, as the programmer, we're responsible for what gets into the entire neural network from the beginning. But what happens in those hidden layers is really not, we don't change those numbers. The neural network itself modifies and changes those numbers. I mean, we set up the framework or the structure of the neural network, and with the explicit or intended purpose of having those numbers, those levers get pushed by themselves naturally. But, in order to do this, it's probably the best thing to do is start looking at this from a class point of view. This is where the object-oriented part comes in. And so what I want to do here is I'm going to start with a class, and we're going to call this, according to the book, layer underscore dense. Okay, and that's a colon. So remember, this is a class defined inside of the Python language. So def, okay, 2 underscores init underscore brackets, and we're going to say self, and let's not forget our semicolon. Okay, and then pass is just so that it's a placeholder for us, so we can continue on. Let's do another one. So def, and it'll be forward. Okay, so really we're talking about the forward pass through the actual neural network. Okay, and again, a path. Remember what we said previously about weights and bias? We talked about them being levers, right? And when we kind of graph this, we're trying to actually have our initial, the very first layers, weights and bias, to be relatively small values. Okay, and so this is going to be no different. We want to keep those values small, so we have a starting place for this. We don't want them to be so big that the graph itself gets too big. We have a huge boundary. So that's what we're going to look at next. So really, let's kind of consider a couple things. I'll go back into this cell here, and I'm going to need to initialize the neural network. So I need to know what my weights are going to be and my bias, but where do I start? Like, who defines that? And so what we can do is actually make this a random number. Okay, and we can call numpy and use this function. So mp dot random dot seed, and we'll just pass for now 0. Okay, and now when I get back into here, instead of just this pass, I'm going to say self dot weights, okay, is going to equal np dot random, okay, and then dot randn, okay, and just finish it off with brackets. Okay, so we know that just this one sample here is of a certain shape, right? And so we want to, in this particular case, you know, all that stuff we talked about, this shape, we have to try to match up, or we have to know those things in the beginning. And so the way I'm going to define that is I'm going to type in n underscore neuron, or input, okay, with it's inputs, okay. And then the next parameter I'm going to need is n underscore neurons. And how many neurons am I going to have? And you notice I'm not hard coding this in there. I'm not giving it an exact number. And now the one thing we need to do within our initialization is be able to pass those through. So if I copy that, and instead of, again, just self, what I'll do is comma, drop that in there. Same thing with this, copy, comma, and drop that in there, okay? And so now in this particular case, we can kind of test this out and see how it looks just by adding in our inputs. And I need to change the spelling on input. And so I'll add this other cell here, and I'm going to do a print. And inside the print, what I want to do is np dot random dot rand, and I want to specify 2 arguments. And if I look at this first one here, you can see I have 4 by 3. Okay, so my argument list becomes 4, 3. Okay, I have 1, 2, 3, 4, and by 3. Okay, so what does this look like now when I run this? So I'll start at the top and make sure that I've got it. And so now this is what we're seeing. This is our new randomized weight values. And I want to point out something. Look at the fact that these are all 0 decimal whatever. Okay, so they're small numbers. And this is what we want to do at the point of initialization, is have smaller numbers rather than large ones. We want to keep it inside a certain small scale. Now, let's suppose that I want to run this one more time, and I'm going to run it again. I'm going to see if I can run this a few times and get larger numbers. I may or may not. And you may, as you're running this, you're going to get different numbers than me. But there is one thing that you can do to ensure that you make these numbers a little bit smaller. And it is simply just go into your print statement here and do 0.10 multiply. Okay, and that should help you get that initial weight values to be less than 1. Okay, so if I actually, let's start from here and run that. And so it's going to keep the numbers down. So if you're getting that, you can go ahead and maybe print out with this 0.10 and multiply it. Okay, if you're not getting the numbers, that's okay. And in fact, I don't need to have it here. What I would rather do is do that at the point of initialization. So I'll go up into my weights and actually do that calculation here. Okay, and I'm going to save this and run it from that cell. And then you see the output there. So when I print it, it's pretty normal for me. Okay, so we're not going to stop there. What we're going to do is now deal with our bias. So self.bias, ES, that's got to be pluraled again. And what we'll do is we're going to say np.zeros. This is going to be 1 by the n neurons. Okay, so I'll copy that, add that here. And like I've said before, whenever you can, copy and paste, because if you spell it wrong in one place, it's going to still work in another. Okay, So we've got our weights and we've got our bias right now. And I have one little correction to make, and I need to actually add in a set of brackets in there. One more set of brackets. The reason I'm putting this bracket around there is this is the shape of the bias. This one is the shape of the end neurons. The way I'm doing this right now stops us from doing a transposition. Okay, because let's look at we've got 4 here, and you can see that we have 3 here. By setting it up in this way, we can avoid doing a transposition like we just previously saw. So let's really quickly look at the forward. Okay, and what the forward is going to be is our input, okay, or inputs, sorry, that's pluralized, but just follow along with me right now. So we say self dot output, okay, is going to equal np dot, okay, and I've got a couple of things that I'm going to pass into that, and I'm going to say my inputs, okay, this here, that's the first one, and then I'm going to say self dot weights, and when I have the inputs and the weights, then I'm going to multiply that by our self dot biases. Okay. And so it's important to understand that my inputs are either going to be the brand new input at the very beginning of the network, or my inputs are going to be the outputs of the previous layer. So it's one or the other. But in this manner, we actually account for both situations. And so this forward is actually the first pass, or the forward pass from the input layer through the hidden layers and all the way to the output layer. And I think what I'll do is I'll take out this line, and I'm going to change this up. So we're going to say layer underscore dense, okay, which is this up here. This is the class that we've created. Okay, same thing here. And what do we want to pass through this? We're looking for 2 parameters that we're trying to pass through this. And again, it is really, the first thing is the first part of the shape of our input. Okay, and we know that we've got 1, 2, 3, 4. Okay, so the first part is 4 features. So this is what our input layer has, 4 features. How many neurons do we want? Right? That's the next question. How many neurons is this going to be? And it can be anything that you want. You can have any number of neurons that you want. I'm going to follow the book. I'm going to stick to that just for your benefit, but really we're going to go with 5. I want 5 neurons. Okay. And then what do I do with this? Now I want to make this layer 1. Okay. And so this is now what my layer 1 is assigned to. Okay. So because we have that sort of freedom of choosing, and if I want to go to another layer and I say layer 2, another, let's say the hidden layer 2, okay, what has to happen though is that my output has to match the input now. Okay, really, really important. In this case, we'll change this output now to 2. We now have layer 1 is an object. And so if I say in this particular box, layer 1, and now I can call my forward method, okay, or my forward function right here. I can call that, and from here, I am going to input originally from my layer 1, I'm going to input X, okay? I'm going to, our starting input layer. And let's print that out. So if I say print, and I want to say layer 1, okay, layer 1 output, okay, because that's what we've got here. And this is just output. So just to be clear, of course, this is not a multiplication. This needs to be changed to an addition, right? We are going to add our bias to our dot product. And So if we go through this, and I actually now run this, and I'll cycle through it. Let me get to here, and let's look at the output of this. Okay, and we see what's going on here. We're actually getting a good output from the original layer. Okay, and it accounts for our bias and it accounts for our weights. And so let's change things up a little bit and look at the next layer. Okay, so if we look at layer 2, what layer 2 is going to, how that's going to turn out is going to be very similar to the one before. Okay, this forward method that we can call our forward function. And our actual argument that we're going to pass through is now layer 1 output. Okay, which is actually this here. Okay, our layer 1 output, we can pass through in this way. So once that's done, now let's look at this. Instead of layer 2 output or layer 1, we can say layer 2 output. Okay. And hopefully what you would expect that if layer 1 has a shape of 4 and 5, that your expectation now is that the next layer is going to be drastically different. Okay, so let's run through this. And you can see now that this is my second layer. Okay, so if I go ahead and comment this out and rerun this, you see that the shape of our new output layer has changed. Okay. So I'm really hoping that you have gotten to this point in the video and that you're following along and everything is okay. But one thing I wanted to do was come back to this page here. This is our Numpy Zeros. Okay, and you can sort of read through the documentation and you're seeing an example right here. We've got mp.zeros5. And what it's doing is it initializes your array to a bunch of zeros. Okay, and in this particular case, it's saying it's the same thing, but it is of data type integer. So that's why you're not seeing the decimal place. Okay, and then you look in this particular example, you're seeing a 2 dash or a 2 comma 1. Okay, so that is the shape of what's going on in that. All right, and there are other documentations. So if you really want to know, I think the best thing is just to type in your search numpy.zeros and you'll find out more specific about that. Okay, let's talk really quickly about the step function. We have two choices here. It's either going to be a 1 or a 0. And we've talked about this in the past. Where does this piece fit in? And here's the answer to this. This is our next sort of sequence within our neural network. We talked about the linear function. We're talking about now, where is my step function fitting into all of this? Okay, and again, I mentioned before that we've got different symbology for this. So, you know, on the left, we've got the inputs, we've got the weights, we've got biased, a linear function, and then the step or activation function. And we want to get a good output in our neural network to our actual next neuron or to the output layer. Now let's consider combining these two ideas. You know, I showed the one picture of them like that, but let's kind of hone in on one neuron. And we see we've got weights, we've got inputs, we've got bias. Okay, and then we've got this output. And what's happening in this output? Well, we've got a combination between two different things, right? We've got the bias, the inputs, and we've got the weights. And you can see that this is the way the relationship between the linear function and the activation function are actually coming together. Again, this is just more levers. And the important thing in here to know is that you can see that anything really on the upper right-hand quadrant of our graph is a +1, and anything that kind of comes down or below that enters into a 0 and +1 again. And so you're seeing the way our activation function is working with the outputs. Okay, and then when we put this all together on an actual neural network, this is what you're seeing. This is what the result in is at every single node, right? We've got these nodes firing and you know, outputting either a 0 or a 1. Okay, and this is really the combination of activation function and linear function together which is producing this overall output from one neuron into the next neuron. But there is actually more to this. There is something that we can do with something called the sigmoid function. And this sigmoid function is actually going to give us a little bit more detail about the values that we're trying to get, okay? Where it's more efficient in terms of the overall sort of detail that we're doing. And you can see here we've got our output and our sigmoid function that is just giving us more detail. And you can see here it's not just 1 and 0, it's actually to the decimal place. And so that's why the sigmoid function becomes so important to us. And you might think, well, why is that really important? And it's for two reasons. Because we're going to use it to calculate loss. And then after that, we're going to do something with optimization. And so that's why it becomes really important. And you can see here now, when we put this into the context of the entire neural network. Now, please understand something. We're not actually going to do a sigmoid function. What we're actually going to do is the rectified linear unit activation function, the ReLU. Okay, this is what we're going to do. And what happens here is if x is greater than 0, then we get an output. If x is less than or equal to 0, then we get 0. And so if you look at it from this point of view here, we're still getting the same sort of granularity out of this that we were getting with sigmoid, but we've got slightly a better modified relationship. Okay, and it's actually more accurate and it's more simplified. That's probably the important thing. It's much more simplified than the sigmoid function. So one issue we have with the sigmoid is something called a vanishing gradient problem. And so we don't really have that with the ReLU. And the other thing is ReLU is much faster. And the reason it's faster, it's simplified, but it's more reliable in the fact that it works. It doesn't have this vanishing gradient problem. Now, because of its ease and its speed and stuff like that, we're going to use this. And then, overall in the greater context, what we get to is the same sort of thing that we were previously dealing with. Okay, it's just now, it actually looks like this now. Okay, so we're using ReLU as opposed to one of the other techniques that we've had illustrated in the past. So in terms of hidden laters and activation functions, I mean, it doesn't get easier than X or 0. Okay, and so that's really what we're going for. Okay, so what I want you to do is don't change your code in doing what I'm going to do, because I'm going to do some things and then modify it and I'll come back to it. So for now, just follow along with what I'm actually doing, okay? And the first thing I am going to do is I'm going to comment out my class. Okay, just going to comment this out, and that's fine there. And maybe I'll move this here above my inputs. Doesn't really matter, to be perfectly honest. And this is what I'm going to do, because now I want to get back to the code and do this ReLU. Okay, so I want to do the ReLU function, but I want to show you a couple things before we do this. So inputs, and this is going to, it's an array, and it's going to have some values. Okay, so this is a really a modified version of ReLU. Okay, and ReLU is rectified linear unit activation function. That's what we're going to do. But then we're going to do it even more simple. Okay, but I want to just kind of do a little quick example. So I'm going to do outputs, and my outputs for right now have nothing. Okay, and then we're going to do this for I in inputs. Okay, and the conditions are, what did we say? It's good if it outputs, if it's greater than 0, then it's going to output sort of this X thing. If it's less than 0, then output is 0. Okay, so what that looks like is if I is greater than 0, then output dot append. And you can sometimes hit the tab button on here to make these things show up better. And you're going to append it to I. Okay, and then elif I is less than or equal to 0. Then output append to actually 0. Okay, and let's print this. So let me back this space. So print, and we'll say output. Okay, we'll print what the output is. Okay, let's run this. And of course, I can't do very much unless I actually include NumPy. So import NumPy as NP, and now I'll run this again. Okay, and of course I did it again. I didn't spell outputs correctly. So you can see here what's happening. In our inputs, we have negative numbers. Okay, I've got -1 and -2.7, -100. Okay, and what's happened is we've ended up, doing this activation function. So this here, this is actually the equivalent to the ReLU. And it's funny because there was a lot of explanation that went into such a small result, but we can actually do this even more smooth than that. So if anything in my number here is less than 0, it gets clipped to just output 0. Okay, and you can see it here, right? This -1, which is right here, is just turned into a 0. Same thing with this 0, and then finally at the end, we just convert that -100. We say, no, we're not going below 0, so just make it a 0. That's all we're doing here. Okay, that's what ReLU in essence is doing. And even again in here, we can simplify that a little bit more. Okay, let's just simplify this to say outputs, append, and right here we can say max, and go with just like this, 0, I, and add another bracket. So that should give us almost the same exact result. In fact, it should give us the same result, and it does. Okay, but we can still do better. Okay, let's get rid of this and clean up our class again. Okay, let me just run that quickly. All right. Okay, and so down here, this is where I'm gonna create this, and it's just gonna be class. And class. Let me give me some space here, get some space. And the way I'm going to do this is just def forward, and it'll be self, comma, inputs. And the next thing I'm going to do is just self dot outputs is going to equal np dot maximum. That tab doesn't work. Max. Okay, there it is. Maximum. And it's the, just like we previously did a minute ago. And that's going to be inputs. Okay. There. So really that's all that looks like right now. For this next part, what I want to do is talk about something that the producers, or the authors, sorry, of the book have done. And I'm going to scroll up and sort of uncover it. Okay, and what they've done is made this code here. All right, and where can I find this? I can probably find it in their actual GitHub. It's NNFSIX. You can actually go to here to their ReLU, and right up here you'll see this note, HTTPS. It's another GitHub repository, and you can go to that. And then actually just download that code if you really want it. Okay. And then I'll show you how to modify it inside the book. Now you can import this if you're doing it on a different IDE. But if you're in a notebook, then basically the best way to do this is the way I'm about to show you. So what I've done is I've actually gone to this and I've copied it all and I put it in the top of my my notebook. Okay, and you can see I've got my import numpy as np and then this matplotlib. You can see the random seed. And then down here, I'm doing my scatter plot, and I'm showing it. Okay, so what we're going to do is let me run this really quickly and show you what is happening here. And the important thing to understand right now is that I have two axes. So that means I actually have two features that I'm comparing against. All right, and so if you look at what this is, I've got 100, let's say, inputs or samples, but I have two features. My in my y-axis and my x-axis. There's two features here. Okay, and so if you don't want to go and get those, then I would say take a screenshot, hydraulically type this out, and then use it however you want. But ultimately, what I'm trying to do with this is I'm getting two different. The most important thing about this is I'm getting this X, this capital X. Okay. And just remember what I said. This is two features that we're going to use for this. Okay. So again, every feature set, okay, is only going to have the two features. All right. So if you were to add up all the red dots, there'd be 100. You add the blue ones, there'd be 100. In the green ones, there'd be 100 dots. Okay. And just for absolute clarity, I'll take this one right here. It looks like it's roughly about minus 70 by minus 70 again. So this blue dot has two features, and it looks to me, if you plotted this with a line, it would probably be minus 70 and again minus 70. Okay, so that's really what I'm talking about when I say it has two features. This is the coordinate result of these two numbers here. And if you think back to previous examples where we said test scores versus GPA, okay, same sort of idea. So right here, what I'm going to do is just follow along here, and it'll make a little bit more sense when you see it. So I'm going to say X and Y. Okay, and when I talk about this, again, I'm talking about my inputs, and then the Y is always the output. This is ultimately my classes that I'm looking for. And so remember that example of whether or not a person based on their GPA and their test scores are getting in as classified as either an officer or they're classified as a non-commissioned officer. But in this particular case, we have a third classification that we're going to do. Okay, so we have this third idea. So now up until this point, you've been just dealing with two classifications, officer, non-commissioned officer, or spam email versus not spam email. You've had two classifications that it's going to be. But in this case, now we can get into doing more than two. So in this case, we're going to pass it three classes. And here we're going to pass it 103. Okay. So truth be told, I probably just could have gone and copied this line right here, because that's really what I'm trying to achieve. And let's move down and look at this. And I think at this point, we're going to do one layer for now. And I will get rid of layer 2 for now. Okay, so I've got layer 1, layer 2. Okay, so now we're down to this layer 1 issue. Okay, and we've got our layer dense. And here's the question for you. And if you don't know the answer to this, don't worry, you're probably not going to be alone. But really think about what this was the last time when we show it. We're saying n inputs. And in another way, we could say features. Okay, and I'll give you the clue to what it is. And I've already said it. We actually have two features. Okay, we've got this feature over here, which would be test scores, and the bottom here would be GPA. So we have two. So what that means is down here, this needs to be 2. Okay, really important that you comprehend that shape. Okay. And for the purpose of this, I'm just going to leave it as a 5 as well. I think that's what they do in the book. And so now I'm going to do this ReLU thing. Okay, so what I want to do is say activation ReLU. Okay, and I'm just going to call the function. Okay. But instead of keep having to call it, I'm going to use it to initialize something called activation 1. Okay, and I'll initialize activation 1 as my ReLU or ReLU function, depends on how you want to say it. I'm just getting used to ReLU. And so the next piece that I want to do here is I want to look at forward. Okay, what happened? There's this forward here, and then there's this forward here. Okay. And so I'm looking at this one here because I've got these inputs now that I want to I want to get. And so when I go to here after my activation, what I can do is I can look at layer 1 forward. Okay. And what does my layer 1 forward look like? And let's have a look at that first. Okay. So layer 1, what I can do is copy that in print and put my layer 1 dot output. Okay, now I can pass because I'm doing a forward pass. Okay, so I actually haven't we haven't got to the ReLU yet. And one little thing that I do need to change here, this shouldn't actually be an output. It shouldn't be plural. But these other ones here are okay. This should be a plural and this one should be a plural. But this self one should be singular, okay? And so when we look at this, what are we really running? So let me see what happens. I'm getting a syntax error, that's okay. And the reason I was getting the error is because I didn't actually compile the previous cells. Okay, so what are we seeing here? We're seeing a bunch of different things. First and foremost, what comes to mind is these negative values. Okay, that's a -3. What's the highest one? I'm seeing a -4 whatever. Okay, so I've got those values. And remember, my goal is to have an output of X or a 0, right? And, to really truly understand this, these are negative values after we've just run the inputs and the weights with the bias, right? But we haven't run the ReLU function yet. Okay, so we haven't done that. So let's go ahead and actually do that. So how do we go about doing that now? And really the answer is going to be, we're going to go below print, the print one, print layer 1 output. And I will do activation 1 dot forward. And what do I pass into forward? What I want to pass into forward is my layer 1 output. Okay. Put this in here. And now let's just, let's print this out. Basically, it'll look almost identical to this with one exception. Okay. We're going to actually now be talking about our activation 1. Okay. And now let me just block this from firing and let's have a look. All right. Now what are we seeing here? We're seeing a bunch of zeros. Okay. And now what I want to do is I actually want to uncomment this out and we can look at an actual comparison. Okay, so we see that these first ones were zeros, and it seems to just be completely truncated, right? But if we just kind of go through and we follow, we notice that a lot of the numbers are not getting replaced. But let's look at this one as an example. Okay, this is 1.5903222. This is 0.159032222. Okay. And so, we've now recreated our outputs to be less than 1, but greater than 0. Okay. And if it was a negative number, it is now just really the equivalent to 0. Okay. So it's important that you understand what's happened here. Here's another one right below it. Okay, it's 1.6403. This is 0.16403. Okay, so you're getting the idea. At this point, what I want to do is just comment this out and run this again. And I'm just left with these values for now, and I'm perfectly happy with that. Okay, so if I were you, I would go and walk away from the computer, take a break, and when you come back, we're going to probably talk about the Softmax. Okay, so that's the next piece we want to do before we get into loss. Okay, so pause your computer, take a break. At this point, what I want to do is talk about the Softmax activation. And you're going to see that the inputs are going to be exponentiated. Then we're going to normalize them. Okay, and then that's going to produce a positive number value output. Okay, and this is really what the math looks like, the formula for this. But ultimately what we're trying to do is combine that to center steps into the Softmax activation function. And this is going to be in addition to the ReLU that we've already produced. Okay, so that's the technical term or the formula for it. But before we get to this, I want to back up because there's a lot that I want to talk about first. And then we'll get back into some coding. What I'm going to do right now is just go and look at a couple things down here in this new cell. It's unrelated to the code that I've written already. I'm just using the cell right now. So if I were to say, if I had a layer output that looked like this, 4.8, 1.21, and 2.8 or 385. Okay, and if we look at that, this output layer kind of doesn't have too much meaning to us right now. And what we want to do is, okay, let's look at a second layer. Okay, so if I copy this and I paste it and I change these values to let's say 4.79, this one I'm going to change to 4.25. Okay, and these are the values in the book. Okay, and so when I look at that, ultimately the goal is to determine how wrong our output is. I know that sounds strange, but perhaps you might think, well, don't we want to know how right it is? Tomato, tomato, I suppose. But for the purpose of this argument, let's say we want to know how wrong our output number is. Okay, so we'll change this to 1. And when we look at this, the question of how wrong is it? How do we know that? We have to actually make a relative comparison to other neurons. Okay, and our issue with the ReLU, depending on how you want to say it, is that the ReLU is just a single neuron. Okay, so it's not relative to other neurons. Okay, so we need to find a way to make it relative so that we know how right or wrong it actually is. And I'm not actually talking about the accuracy of the output, because really, this output, layer output and layer output 1, accuracy, they're fine. They produce the number they're supposed to produce. But in terms of how right or wrong they are, that's a different question. So let's look at a neural network again. And what are we trying to do here? We're feeding an input into this neural network. And you can see we have outputs here, but ultimately what our goal could be right now is to create a probability distribution. And, you know, a perfect classification would be 1.0. Okay. And also I would argue that a perfect classification would be 0.0 because it either is or isn't. You know, it's a binary probability distribution, 1 or 0. But typically what you're going to see is something that is going to be in between 1 and 0. Okay. So, you know, we continue to do this, but, you know, what does that mean for this? How do we measure the right or the more right or the more wrong? Okay. So you might think, well, let's just take the value of each neuron and divide it by the total number or the total value of that layer of neurons. Okay. But unfortunately, that's not going to really do it for you either. And the reason is because you still got to deal with those negative numbers. Okay. And you can see here with the ReLU, you're still getting the negative value. So we can't discount that something has a negative value and therefore is just set to 0 because it still has meaning. That negative number has meaning. Okay. So we could, because, you know, our negative values are just getting appended to 0. And that's not really ultimately going to help us out. And so you might think, okay, fine, we could just do a linear activation. Just do that again. But we still have to address the negative number issue. Okay, well, what about just doing an absolute value or doing a squaring of the number? And again, if we do that, we can't in the future optimize that number. And we haven't talked about this back propagation issue yet, but you know, it does exist. And that is going to be a problem if we try to come backwards through our neural network and we've got these numbers that were squared or they're absolute values, because, you know, -5 and +5, although they're both 5, their sign or their negative or positive value has actual meaning. So the thing that we can do is this thing called an exponential function. Okay. And this actually does solve our problem. And we've got Euler's law here. Okay. Or Euler's number. And it's this 2.718. Okay. And here's, you know, the formula and here's the fancy math to it, right? And what this actually does is allow us to address that positive or negative number while still keeping its relative meaning. And that's really what we're trying to do. Keep that relative meaning. Okay. And this allows us to normalize the number as well. Okay. So this is really how we're going to be able to address this. Now, this is all the high level technical piece to this, but it's actually, when we get to the code, it's actually quite simplified. Okay, but this is really how we're going to address it. So if we go back and we look inside our cell, I'll get rid of this. And let's look at what that Euler's number is. So E equals 2.71822846. Okay, so that's what that is. Or if you import math and then you say capital E equals math dot lowercase e, and then you can sort of comment this out. Really quickly, you know, if you're watching this, you don't have to do this piece. You can do it if you want to, but I just want you to understand what I'm really trying to do here. And so we're going to exponentiate the output layer here. And the way I'll do that is just simply I'm going to say exp underscore values, exponentiate values. And really just putting this into array. And now we have to iterate through this and then exponentiate each of the values inside that output layer array. And so we need a for loop. So our we'll do for output in layer, this one here. Okay, semicolon, and then we're going to say exp tab. That worked, surprising. And then append. And in the append, the way we're going to do this is capital E, and you do the double multiplication for exponentiation, and then output. Okay, and then what do I want to do? I just want to print this. And my exponent value. And we're going to have a look at this and run that. And you can see that's what's happening here. Okay, so these are exponentiated values. And the next step that we have to do is actually now to normalize them. Okay, that's the next piece we have to do is normalization. So we're going to do something called normalization. And normalization is we're going to take the neuron's value and we're going to divide it by the sum of all of the neuron outputs in that particular layer. But before that, we have to address the negative value number. Okay, so we'll do exponentiation first, because even if we don't, we try to normalize a negative number, we're still going to get a negative value output, and that's not what we want. Okay, we don't want the negative number. So as you know, we want to do the exponentiation first, then we're going to do the normalization. So after this thing, we're going to do norm. We'll call this one norm base. And this is just going to be a sum of the exponential values. And so we'll do sum and these values here. Okay, that's our norm base. Then we're going to make a norm underscore values. And again, you don't have to do this piece because we're going to actually go back and modify our code from previously, but just follow along and try to understand what's going on. Okay, so I'm just going to make this norm values array. And now let's go we have to iterate through this. So value in exponential values or exponent values. And we're going to do norm values dot append. And in the append, now we're going to say values. Okay. And where's our values? What we want is this value here and here to be divided by our norm base. Okay. And then from there, I'm just going to do a couple print statements. Okay. And I'm going to print our norm. It actually should be values. And I'm going to print my sum of the norm values. So this piece is going to show us the normalized values in the sums. And then this one is going to show you that it actually does add up to almost 1. Okay, so let me go ahead and run this. And you can see what's happening here. This was our first set of values. This is now our exponentiated plus normalized values. And then the sum of all of this is this final number right here, which is almost, I mean, it couldn't come any closer to being 1 if we tried. Okay, so that's where we are with this piece. So this in itself is just how raw Python is going to do this. But we can, in fact, we can go to here where we've done the math. And let me move my import up top. And below that, I want to import NumPy. Okay. And there's a reason I want to do that. And it's because I want to just change up this code a little bit. So what I can do is actually get rid of this here. And then over in our values, I can do np.exp and really apply this to the layer output, okay? So if I put this inside here, we're getting really the same thing. And here I can actually go in and clean all this mess up too. And what I'm gonna do is say norm, okay, which was these ones. Norm values will be equal to x values divided by np.sum of x values. Okay, and let's go ahead and run this. All right, and so look at what's happening here. Same sort of output altogether. So believe it or not, that is the exponentiation and then the normalization. It's not that difficult, but I did show you in a Python, pure Python way, and then I showed you using NumPy. Okay. And so again, what did we do? We went input, exponentiate, normalize, and then to an output. Okay. So, we're taking, let's say, for example, these three samples, and we're exponentiating them. And then we're going to normalization again, and we're getting these positive values as outputs. And you can see here that these numbers actually do add up to a value of 1.0. And so this is our softmax. And, here is sort of the fancy formula to our softmax function. How do we get this to be more of a batch? And so what I think I'm going to do is just convert this to a batch. Okay. Sorry. Make this into a batch. And I think I'll just copy these and then update their values. There. So now I've got this as a batch. And I don't need this anymore because NumPy is taking care of it. I don't need this. In fact, I don't even think I need this anymore. Turns out I just need this. Okay, so let me comment this out. And I'm not going to print the normal values. Let me comment that out. And I want to just really print my exponent. And do this. And let's see what happens here. Let me comment that out as well. Okay, so this works. The exponentiation of our batch of output layers is actually working. So that's good. So I want to actually, from this layer output, I want to get this converted into three values, right? And so if I leave this line in here and let's say very similar to this line here, but I'm going to put in a new line here, and it's going to be print, and we'll say np.sum. And what is the sum of is my layer outputs. And so what am I going to get when I do this? Let me comment this out as well. Okay, let me print this out. And I'm getting the sum of my layer outputs, which is not really what I want. I want actually 3 output values. So for starters, I can do something here. And in here, I can add this other parameter to my sum. And it's to get the axis, or really it's the column that I'm after. So if you look here, this 4.81, 8.9, 1.41, it's going to give me 3 outputs, but it's going to do a sum of the 3 columns themselves. So we'll do axis equals 0. And then let's look at that. And you can see what's happening here. So this is the summation of these 3 columns. But that's not really what we want. I just wanted to show you can do either sum or column or row. So we actually want the row. Okay, and we change this to 1, and then we rerun this, and you can see that the sum of this first layer here is put into here. So all 3 of these, so 8.391 is the sum of what I've got highlighted here. Okay, so we're looking literally at the shape of this. Okay, we've got the way this matrix is laid out. Okay, and so we don't want to really get too deeply involved in transposition and all that kind of stuff. So the one thing that I can actually do is just add this other parameter to this this function. And what it's called is keep dims, like keep dimensions. So keep dim, and we're gonna with an S, keep dims, and we'll set this to true. So we're saying keep the dimensions of this thing right now, okay? And so let's go ahead and run that, and you can see that the shape of this is really outputted in the same shape as this one here, okay? But what I actually want is my normalized values, right? That's what I really want to have. And so what I'm going to do is take this keep dims. Now I'm going to take normalized. I'll uncomment my normalized values. And I'll keep everything the same as what you're seeing here, but I'm going to add now this whole section here. Okay, so I'm going to copy this, and I'm going to paste it in here, but I forgot a comma. Okay, and I'm trying to do that now with my normalized values. And so if I run this, let me now comment out. So that one's commented out, but let's look at this. Let's print out our normalized values. And there it is. Okay, and let me take out, I'm going to comment this value here, or this line, and just rerun that. And so now we've got our normalized values. I've got this issue now with exponentiation, or these exploding values. And you can see that over time, these values can get just humongous. So I have to find a way to deal with that because I could end up getting an overflow, and that's going to cause a problem for me. So I don't want this overflow. And the way that I'm going to prevent this is in this way. So what I'm going to end up doing is actually removing my largest value from the actual equation. So you see here, I removed the 3. And what it does is it gives me a sort of a different value. And as time goes on and I'm back doing this exponentiation, what it does is it brings it down to a normal level, almost to a maximum of, let's say, 1 or 0. It bounds the range between 0 and 1, really. And so that's what I need to do with that to avoid the overflow in sort of the explosion of values. Okay, and you can see here in this example, what's happening is I've got my largest number, 2.30. I'm removing it, and then I'm going into my exponentiation. I'm performing that particular operation, and then I'm going to go and start doing the normalization. And what you see is you might be worried, okay, well, you've completely changed the dynamic, but in the end, I'm actually getting the identical output of what I previously had. So what I'm going to do now is actually clean all this up. I don't need it. What I want to do is go back into here and modify or add this this new class here to our project that we've been working on previously. So what I'll do is just, I'm going to comment it out for now. And let's go back up into here and see what's going on with what we left off with. So we just basically left off with the activation ReLU, and let's continue on from there. For now, what I want to do is take this line. I'm actually going to, I'm going to move this down. Put that in there, down there, just kind of out of the way. And I don't need this anymore. So I'm going to take that out and I'm going to clean up this. Let me just do a little bit of house cleaning here. And so now what I want to do is make this activation Softmax. So we're going to say class activation and underscore Softmax. Okay, so we've got this, and let's not forget the semicolon. Let's go to here, and we want our forward again. Okay, so forward, and in here it's going to be self, comma, inputs. Okay, and from the inputs, you know, basically very similar to what we did down below. Okay, we're looking at this this idea here, this exponential values, but let's just go up here and kind of keep it separate as cleaner code. And in here, we're going to say np dot exp, and right away we're just say inputs. Okay, and the thing is this: we can't take just the raw inputs, right? Because don't forget, I need to get rid of the largest number of the two. Okay, so I'm going to say inputs minus np dot max, and that's going to be another function, and this will be inputs. Okay, now we have to be careful here. Okay, I can't, if I do it in this way, don't forget, we up here, we go here, we have batches of data, right? I can't just, if I do this, what it'll do is just grab the largest value of all of it and then subtract it. So I need to be explicit on what I want it to do. So in this case, I'm going to say my inputs and then axis equals 1 and keep dims. Okay, so keep dims equals true. Okay, and then you should have 2 brackets on the end there. So yeah, that looks about right. You know, and really the objective here is to not get the overflow or the exponential explosion, right? That's the whole point of subtracting that max. Okay, so what's next here? So next we want to deal with the probabilities, and we want to keep the rows and the dimensions. So this will be probabilities. Okay, probabilities, and this will be exp. Let's see if tab works good. It did. Divided by our np dot sum. And what's inside here is going to be our xp. Okay, our exponential values this year. And we're going to keep that, like I said, the rows and the dimension here. So it's really just this here part again, right? And we're good. And then finally now it's going to be self dot output, and that's going to be our actual probabilities, just like this. So next thing I want to do is I'm going to keep this spiral data, and I just want to add samples equals 100. And then I can do this classes equals 3. Okay, and that's what we're going to stick with. And I think what I'll do is I'm going to get rid of this. Actually, not all of it, just this line for now. Okay, give me some room. And this is going to be dense 1 is going to equal layer dense. And the shape of this, remember, I've got 2 features that I want to use. So it's going to be 2, and we'll go with 3. Okay. And I'll keep the this line 3 here. And now I'm going to do another dense 2. And this is going to, same thing here. But remember, this number here, this 3, has got to match the next layer. Okay, it has to match. And I might as well just keep 3. That's what the book says. And so this, don't forget, output layer, or what we're saying here, the number of layers or neurons here has to match this parameter as well. And below this is going to be, I'm going to copy this, but this will be activation 2. And it's not going to be this one here. It's going to actually end up being activation. Nope, not that one. I want it my Softmax. Softmax. And let's just be perfectly careful. Okay, so that's what that one's going to be. And let's keep going. So I've now got dense. Okay. Dense 1 dot forward. Dense 1 dot forward. And I'm going to pass in our capital X. And then we're going to do activation 1. And this activation 1 again will be forward. And in our forward, we've got our dense 1 output. Okay, and that's that line there. Now let's just copy and paste all that. And then we can just do some editing. That's a little bit better. So now I've got dense 2 that I want to do. Dense 2 forward. And instead of that, I want activation 1 instead of my X. Okay, I don't want X in here. I want activation 1. But the activation 1 dot output. Okay, and then from there, I want activation 2 forward becomes dense 2 output. So this dense 2 output. Okay, and then I can do a print. So within my print statement, what I want is my activation 2. Activation 2 dot output. And because there's 300 of them, I don't want 300. What I want is in my square brackets, I'm going to just specify the first 5. So put my colon and a 5, and then let's run this. Okay. I've got a 1 minor error. And the error is probably that after I created the Softmax, I actually didn't run it. And so let's go down to the next thing. And you can see the error cleared because I didn't run it in the previous cell. But now I have a different one. It's just complaining about the this part here. And I can take those out and it shouldn't have any effect whatsoever. So if I run that, that error goes away. I still get the output that I was looking for. Okay. Now consider the outputs were random from the beginning, right? When we created this, these are all random outputs. And then when you look at this, you see, you know, these almost, you know, they add up to almost 1 in each particular case. Okay, so our actual outputs are also random. We've covered an enormous amount of ground in this particular video. And so what I'd like to do is actually end it there. There are things that still need to be done, right? We still need to calculate our loss. And of course, the loss, what we talked about earlier, becomes more important than accuracy because it really becomes a measure of how our confidence. It's a measure of our confidence in the actual proper output. And so what I want to do is stop there, and next week when we come back, start picking that piece up and talk about our loss function and really determine what's our level of confidence. So we've done a lot now, and so I do want to just leave it there. And when we come back, we'll digest all that information as well next time around. Okay, so hopefully you got to this point, you understand what's going on, and we'll continue this on in the future. But for now, get to this point, and we're good to go for now. All right, so thanks for watching, and I'll see you next week.